In this video, we're going to take a look at various ways of solving these differential equations by replacing one of the variables. I'll start with an example to explain what I'm talking about. We have x plus y dx plus x dy equals 0. You'll notice real quick that it's not separable. However, if you call this piece m and this piece n, then if I do m sub y, I'm going to get 1. And if I do n sub x, I'm going to get 1. So it's an exact equation. That means to get my answer, I can simply integrate. And if I do the x plus y dx part of it, I'll get x squared over 2 plus xy plus a constant that is a function of y. And on the other hand, I will get x dy will simply equal xy plus a constant that may involve x. So looking upon this, I see that my f of xy is xy. So my answer is xy plus, I see that cy is 0, but cx is x squared over 2. And that, of course, is equal to a constant because the original function was set equal to 0. Now, if I want to, I can simplify it a little bit by multiplying everything through by 2. I get 2xy plus x squared equals, and the constant will just absorb the multiple of 2, and I write my answer that way. Now, I'm going to use this as an example of what I want to do. And my example to solve this in a different method will seem way more complicated, but it's an easy example to do for the first one to explain this kind of stuff. So, we're going to redo example 1. This method will work for non-exact equations too. So let me go back to this. X plus y dx plus x dy equals 0. Now what I'm going to do is I'm going to factor an x out of the first piece. And the second piece I'm going to leave alone. This seems unusual, I understand. Now, the reason I did this is because what happens when I factor out the x, I'm left with the 1, and then I'm left with this y over x piece. My goal here is to replace y over x with a different variable, and then somehow throughout the entire problem, eliminate y as a variable and change it to my new variable. If all that makes sense, let me show you what I'm talking about. The substitution I'm going to use is this. Substitute u equal to y over x. Or better yet, I'll have ux equals y. Now let me take the differential of both pieces. So when I take the differential of ux, I have a product rule. And the way it will look will be u dx plus x du, and that equals dy. Now let's go back to not the equation that I pulled this thing out of. This here, the importance of this will be seen later. The fact is I have a factor of x there, and here I probably should have put x times 1. You see that you have an x in both pieces. In fact, if I were to divide out the x, it would look like this. 1 plus y over x dx plus dy equals 0. Now it seems a little bit simpler. If I replace that with a u, like I intend to do right here, replace it with a u, I still have to replace the dy portion of it with all of that stuff. But I'm not going to work this equation this way. I'm going to start with the original equation. And how does that work? All right, so let's go ahead and put my x plus y dx. Well, let me rewrite it. X plus y dx plus x dy equals 0. Now I'll go ahead and replace my y with ux. So x plus ux dx plus x times, and then my dy is all this stuff. U dx plus x du, and of course that equals 0. Now I'm going to multiply this through, and then I'm going to collect my dx's and all that kind of stuff. So x plus ux dx plus ux dx plus x squared du. You'll notice right now there's no sign of y anywhere. It's only u's and x's. So I have successfully replaced y with u. Not directly, but in a way I have. Now I'm going to combine all the ux's together, and I'll get x plus 2ux dx plus x squared du equals 0. Now let me factor out an x. Now you see that we have a separable equation. And that's the thing that we're going to be having to work with. Even for non-exact equations, this will happen that way. So I'm going to do like I normally do. I'm going to take the other stuff to the right-hand side. So I get x times 1 plus du dx equals negative x squared du. And then I'm going to go and get u's on one side and x's on the other side. I think for the purposes of integration, I may make some certain choices here. So let me divide by negative x squared. That way I get negative 1 over x dx equals 1 over 1 plus 2u du. Now, of course, the stage is set to integrate. So I'm going to have negative the integral of 1 over x dx equals the integral of 1 over 1 plus 2u du. Now, if you choose a third variable and say v equals 1 plus 2u, the dv will be 2 du, and what I'm talking about is that in the end, you're going to get 1/2 the natural log of the absolute value of 1 plus 2u plus a constant. On the other side, you're going to get negative natural log of the absolute value of x. Now I'm going to multiply through by 2. So I'll get negative 2 ln absolute value of x equals ln 1 plus 2u plus c. And I think if you were to try to solve this in the most compact form, what you might do next is the following. I'm going to take this negative 2 and put it as an exponent. So ln x to the negative 2. Notice that when you square x, it won't be negative, so I could drop the absolute value symbols. On the other side, I have ln absolute 1 plus 2u plus c. So let me go ahead and, seeing as I have an x to the negative 2 over here, or maybe I should have left it as negative 2. It really doesn't matter. I'm going to take that stuff to the right and put my constant over on the left. So I'll have ln 1 plus 2u plus ln x to the negative 2. And that was actually a minus. But I could take the negative out of that. I'll have ln 1 plus 2u plus ln of x squared. Now, before I'm finished, let me go ahead and replace my u, put it back to what it was before. So let's go back and see what that u was. U equals y over x. So u equals y over x. Let me go ahead and plug it in. I get c equals ln absolute 1 plus 2 times y over x plus ln x squared. Now I'm going to combine the natural logarithms, and I'll get ln absolute 1 plus 2y over x times x squared, and all of that's inside the natural log. I'm going to multiply the x squared through. I'll get ln absolute x plus 2xy, and that equals a constant. I'm going to take e to both sides, so I get e to a constant equals the absolute value of x plus 2xy. And let me correct something that I made a mistake on here. There's an x squared there. Now, it's true that if you take the absolute value of something, you can get a plus or minus constant on this side. So I'll get plus or minus e to a constant equals x squared plus 2xy. And then if I allow c to be this whole thing, like just some constant that could be positive or negative, I could write my final answer like this. C equals x squared plus 2xy. And you can see that I get the same answer as before. Of course, I went through a lot of effort to make it look exactly the same. But if you look at the steps. There's a lot of steps here. Whereas in the original problem, that it was an exact equation, look how short of an answer that is. So this may seem like, why would you possibly do something like that? Well, the reasoning is for non-exact equations, this method is going to be the only method that will work. So let's do a little theory. It's not really theory, it's more derivations than anything else. But recall, when you write something like this, you have to remember that m is a function of two variables, and so is n. Now, what you saw before is that I pulled something out of the equation in the first example that I did, or at least the second way that I did it. I factored out an x and I made some notations about it. Well, we want a very specific kind of function for both m and n to be. So consider the following. If I take and replace t or x with tx and y with ty, if you can somehow factor out that t in one way or another, and you can do the same thing for y and pull out the same amount of t, then these things are going to be compatible for this method. In fact, we refer to them as homogeneous functions. So long as it's the same alpha that you pull out of both of them. Now, that's not the same as a homogeneous differential equation. Those equations are the ones that are set equal to 0. So our equation is homogeneous, but homogeneous functions are ones that act this way. So, and I probably should say of the same order because I'm pulling out the same t to the alpha. So this is for anything that you might have attached to both of them. So now let's go one step further. So suppose m of xy and n of xy are homogeneous. I don't want to leave it at that I want to put functions. Okay, if that's the case, then here's what I could do. I could take the m and I could rewrite the first piece as x times 1, and the second piece is x times y over x. Because of the homogeneousness, I could rewrite this then as x to some power m of 1 comma y over x. And the other one, n, I'll do the same thing, x times 1 comma x times y over x. I'll factor out that x, and I'll get an x to the alpha. Whatever, I don't know what alpha is. I'm just saying I can pull it out. Well, then the equation, our equation, m of xy dx plus n of xy dy equals 0. I'm going to do this x to the alpha business for both of them. So I'll have an x to the alpha, m 1 comma y over x dx plus x to the alpha, n 1 comma y over x dy. Then you divide both sides by x to the alpha. So away it goes, and we're left with this type of an equation, m of 1 comma y over x dx plus n 1 comma y over x dy equals 0. And at this stage, you would go ahead and set u equal to y over x, which is the same as ux equals y. I chose y over x because of this appearance. Now, it may be easier to, instead of pull out the x, to pull out the y. And then on the first piece, you'll have an x over y, and you proceed as you need to. So anyways, with ux equal to y, then we know you'll do this enough to where this will be an automatic. You got u dx plus x du equals dy. Then, if I make these replacements into my equation, I'm going to get m. I don't want to replace the dx. It's the dy I want to get rid of. I'm actually going to end up getting rid of y. So I have 1 comma u dx, and then plus n of 1 comma u dy, and that's all this stuff. For m, the only variable in there is u, and for n, the only variable in there is u. So, I can think of this first thing as just a function of u times dx and a function of u times u dx plus x du equals 0. I'm going to multiply this nu through. I'll get m of u. Now, when you multiply it through, I'm going to get an n of u times u d of x, or u n of u dx. But then I'm going to get nu times x, or x n u du equals 0. Now, can you see it? It's separable now. I could divide by x and also divide by that stuff, and I'll have a 1 over x dx plus n of u all over m of u plus u n of u times du equals 0. So there it's completely separated now. So I've taken an equation of who knows how much complexity. As long as I have this stuff going on, I'll be able to make it a separable equation. So let's use that for our next example. So let's try x dy over dx equals y plus the square root of x squared minus y squared. Now, to make it like any of the other types of problems, I'm going to multiply through by dx. So I get x dy equals y plus the square root of x squared minus y squared, all of that times dx. But I could try to factor out an x from everything. Let me see if it works. I forgot a crucial piece of information, which is that x is greater than 0. If I factor out an x from this part of it, then, since x is greater than 0, we'll get the square root of 1 minus y over x, and that quantity will be squared, dx. Since you can see an x being able to be pulled out of both of them, and there's my u sitting right there, I will let u equal y over x, which is the same as ux equals y, or du, let me do it straight up, I'll have u dx plus x du equals dy. And I wouldn't plug it into this thing. I'm going to start with the original one and work it. So I'll have x dy over dx equals y plus the square root of x squared minus y squared. And then I'll multiply through everything by dx. So I'll get x dy equals y plus the square root of x squared minus y squared dx. Then the actual substitution that you use, unless you do choose to do all this stuff, divide out the x and then do it this way, I guess, which is what we'll end up doing anyways. But, so you could do it before or after, it really doesn't matter. It's the y that I want to get rid of. That means on the left I'm going to have x, and I'm going to replace dy with u dx plus x du. And then the right hand side, y is going to equal ux plus the square root x squared minus u squared x squared. And that's attached to dx. So I guess it's not a bad idea when you can do it. Take any opportunity you can to make things simpler for yourself. I can factor out an x out of this square root. Since it's positive, it comes out. And out of the right side, I can have x times u plus the square root of 1 minus u squared dx equals x times u dx plus x du. Cancel out the x's. And now let me go ahead and do some combinations of things. I have u dx plus x du equals u plus the square root of 1 minus u squared dx. If I subtract u dx from both sides, notice that I'm going to get rid of that u. So I'll have the square root of 1 minus u squared dx equals x du. And now I'm going to separate variables as normal. I'll divide by 1 minus u squared. So I have 1 over the square root of 1 minus u squared du will equal 1 over x dx. And it's time to integrate. Of course, on the left side, you should know that that is arc sine of u. And on the right, it's ln. The absolute value of x is not needed because x was told to be positive, so we got ln of x plus c. And then if I want to get u by itself, say I want to explicitly solve for u, I could take the sine of both sides and get u equals the sine of ln of x plus c. We're not quite done. Remember that u equaled y over x. So I'll put the y over x back in. Y over x equals sine of ln of x plus c. Multiply through by x. Should I want an explicit solution, I'll do that. Another type of substitution is involved with the Bernoulli equations, or the Bernoulli's equation. And the general format for such an equation looks like this. Remember, the idea is you'll be given all sorts of specific equations. We're going to try to classify them into certain types of solutions depending on the equations that we have. So, when n equals 1 or 0, we can use the integrating factor that I showed you before. So when n equals 0, 1, when n is 0, you just have a g of x over there. When n is 1, I'll have a y in both places, and then I can subtract g of x times y to have a function of x times y is equal to 0. So either way, you can, in fact, if n is 0, it's separable anyways. So we're going to assume that n does not equal 0 or 1. N can be any real number except 0 or 1. Okay. The substitution we want to use is a substitute u equals y to the 1 minus n. This may seem like a crazy thing to do, but watch all the stuff that happens. When I have u equals y to the 1 minus n, if I take the derivative with respect, well, actually, let's just differentiate using differentials. So I'll get du equals, I'll bring down the 1 minus n, y to the 1 minus n minus 1 times dy. And, of course, the 1's cancel, and I get 1 minus n, y to the negative n, dy. If I divide by dy, I get du over dy equals 1 minus n, y to the negative n. Now let's go back to the original equation. Dy over dx plus f of x y equals g of x y to the n. Remember, these functions, this f of x means that this is just a function of only x, and g of x is a function of only x. So this is somehow likely to be kind of separable. Not quite, but they're kind of factorable. And then what I'm going to do is put this thing in here. You'll recall that this part right here, the dy over dx, can be rewritten as dy divided by du times du over dx. That's the chain rule. Plus f of x times y equals g of x y to the n. Now, over here where I have du over dy equals that stuff, I actually wanted the upside down version of it. So the upside down version of this dy, or the du over dy, is going to be y to the n over 1 minus n times du over dx plus f of x y equals g of x y to the n. Now the first thing you'll do is divide through by this y to the n. So we end up with 1 over 1 minus n du over dx plus f of x times y to the 1 minus n. Remember, when I divide by y to the n, I have to do it to all pieces. And that will equal g of x. Now, I'm going to replace the y to the 1 minus n with u. And I can multiply everything by 1 minus n to give me this form of the equation. So notice it's in the format we want. This piece right here, that's a function of x. A function of only x. So it takes the format of the equations we did before. At this point, you would use the integration factor, let's call it INT, FAC, would be e to the integral of 1 minus n f of x dx. And then proceed there like you did before. Let's do an example. Y to the 1/2 dy over dx plus y to the 3/2 equals 1. And I will divide everything by y to the 1/2, and I'll get dy over dx plus y to the 1 equals y to the negative 1/2. Now, I could take this y over there and possibly work with it and have a separable equation, but to illustrate the method, which will work for more than just those that are separable, we could do u equals y to the 1 minus n. The n here is 1/2. So we're going to do 1 minus negative 1/2. And so we'll get y to the 3/2 is what I'm going to allow u to equal. And then when I do du, that's going to equal 3/2 y to the 1/2 dy. I want dy over du actually. So I get 2/3 y to the negative 1/2 equals dy over du. Okay, with all that stuff in place, let me go ahead and solve the equation. So as before, dy over dx plus y equals y to the negative 1/2. If you rewrite the dy over dx, you're going to get dy over du times du over dx plus y equals y to the negative 1/2. Let me replace the dy over du. That's going to be this 2/3 y to the negative 1/2. So 2/3 y to the negative 1/2 du over dx plus y equals y to the negative 1/2. You can see that the y to the negative 1/2 is going to eliminate that one on the other side, and I'm going to divide by y to the negative 1/2 or multiply by y to the 1/2, whatever it is you want, and also multiply by 3/2. So I'll get du over dx plus 3/2 y to the 3/2, and that will equal 3/2. So now it's just like the ones we did before. Your integrating factor, your I dot f, will be e to the integral. Notice that the 3/2, I think I'm jumping ahead of myself just a little bit right here. U equals y to the 3/2. So we get du now it's just like an equation we had before. Now you'll still use for your integrating factor the integral of 3/2 dx. You see now your variables are u and x. That'll be e to the 3x over 2. And then go from there. I will leave it to you to get the answer of y to the 3/2 equals 1 plus c e to the negative 3x over 2. We call this example 4. Determine the solution to the previous example, if you know that y of 0 equals 4. So suppose you have this initial value given to you. Once again, I will leave this to you, and the equation will have the solution, y to the 3 halves. I mean, all you're going to do is replace c with a number. It will be 1 plus 7e to the negative 3x over 2. For my last example, I want to do an example of one that doesn't have really a form of anything we've done so far. And what I'm talking about is try to use a substitution which seems natural in the context of the problem. And what you might do with this is you might notice that this is equal to 1 minus x plus y all over x plus y. To me, it seems evident that using a u for x plus y is the thing to do. Notice that I can't factor out an x or I can't factor out a y and get anything going there because that 1 is stopping me. But it wouldn't be so bad to have a 1 minus u over u. I could work with that. So let's go ahead and let u equal x plus y. Then du is easy to find. That's dx plus dy. Now I'm going to either substitute, I will put u in for x plus y, but I want to decide whether I want to replace dy or dx, and that's all going to depend on what's easier to do here. I don't want to just try to plug in dy or dx until I see which one's easier. So I'm going to take this equation and let me go ahead and replace those with u. Cross multiply to get u dy equals 1 minus u dx. And now I'm going to try to figure out which one's easier to use. Is it going to be dy or dx? And if I go and try to get rid of dx, I am going to do a FOIL method. Over here on the left side, it's much easier as far as I can see. So I am going to elect to get rid of dy. That means I will replace dy with du minus dx. And the other side is 1 minus u dx. So let's combine everything I got together. I have u du minus u dx equals 1 minus u dx. Well, this gets very easy real fast. At this stage, I see that if I add u dx to both sides, I'm actually going to cancel those away, and I'll be left with just dx on the right side, and on the left side I'll have u du. Well, now we can just integrate. And I get u squared over 2 equals x plus a constant. And it might be a little easier if you multiply through by 2 and you get u squared equals 2x plus a constant. And then now I'm ready to replace u with x plus y. And that finishes off the problem.